What's up guys, this is Masi, welcome to my channel. In the previous video I talked about acids and bases, so I defined what acid means, what base means, and what are the differences between Arrhenius acid and base definition and Bronsted and Lowry acids and base definition. And also I defined conjugate acid and conjugate base. We said conjugate base is everything that remains of the acid molecule after a proton is lost, and then conjugate acid is formed when the proton is transferred to the base. So whenever we have conjugate acid base pair, it consists of two substances related to each other by the donating and accepting a single proton. If I go back to the equation I showed you last time, we have this equation, HA, which is an acid, plus H2O, water, gives us H3O plus, which is hydronium ion, plus A minus. So hydronium ion is conjugate acid in this case, and A minus is conjugate base. As you see here, acid, when it lost the proton, it becomes A minus, which is the conjugate base. And water molecule, when it accepts the proton, it's going to be H3O plus, which is conjugate acid. Then we can write the acid dissociation constant. It means that, acid, when it loses the proton, it results in having conjugate acid and conjugate base. So when we write this reaction, we can write the dissociation constant as well. Dissociation constant is basically written only for weak acids and weak bases. I will explain weak acids and weak bases later on, but that's how we write the Ka. So it's going to be the products divided by the reactants. H3O plus times A minus divided by HA. The reason we don't have H2O here because that's liquid, and we don't write liquid in the equilibrium formula. We just write equals and also the gas phase. We don't write it for liquids, we don't write it for solids. So the concentration of products divided by concentration of reactants. So Ka, acid dissociation constant, is going to be H3O plus times A minus divided by HA. Or you can also write it in this way when you show only the proton, where Ka is called the acid dissociation constant. So if you have a strong acid, you have large acid dissociation constant. If you have a weak acid, you're going to have a lower number, smaller number for acid dissociation constant. It means that acid dissociation constant means the ability or the affinity of acids to lose the proton. If they have high ability or high affinity to lose this proton, they have large Ka. If they have weak affinity to lose proton, it means that we have lower numbers for Ka. Let's see some examples. These are the acid dissociation or ionization reactions. Write a simple dissociation or ionization reaction omitting water for each of the following acids. First one is HCl, hydrochloric acid. You can write it like that. Hydrochloric acid gives proton plus Cl minus. Acetic acid, HC2H3O2. So it becomes proton, and the rest of it is going to be whatever you see here with one less hydrogen and the negative sign here. NH4 plus, when it loses the proton, it's going to be NH3, ammonia. And last one is the aluminium ion. We have it here. When it loses the proton, it becomes like that. Oh, there's one more. It says the hydronium aluminium 3 ion, which is AlH2O6 and 3 plus. Although this formula looks complicated, writing the reaction is simple if you concentrate on the meaning of Ka, removing a proton which can come only from one of the water molecules. Leaves one of these molecules to OH minus, and we have 5 H2O molecules attached to the aluminum ion. So it becomes like that. Al H2O6 3 plus is going to be H plus, which is proton, plus Al H2O5 OH 2 plus, because it becomes 1 negative, so 3 plus minus 1 is going to be 2 plus. That's how we write this acid dissociation reaction. I hope you enjoyed this video. Please like this video if you find it useful, and please don't forget to subscribe this channel. And if you have any question, leave a comment. I get back to you as soon as possible, and I will come back soon with another video. Have a great day.